Good day. This is Swaminathan SM, Assistant Professor, EC Department, SNSCT. Now we are going to discuss about VLSI design subject. So first, what is the expansion of VLSI? Very large scale integration. So that is the expansion of VLSI. So today we are going to discuss about the first topic of first unit, CMOS Fabrication pwell process. Before we are entering into the topic, we just discuss about the basics of MOS transistor. So first one, what are the outlines of today's topic? First one is introduction and levels of integration based on the Moore's law, because engineering is bounded by science. Here VLSI design is bounded by the science called Moore's law. Next, design of abstraction levels. Third one, why the name is called MOS, metal oxide semiconductor. Then what are the two mode transistor action? Next, go for activity. Next, two mode action, enhancement mode, depletion mode. Pwell process with different masking levels. Next, using the pwell process, how can we design the CMOS pwell inverter? Next is summary. So this is the outline of today's topic. So first, levels of integration. First one is integration levels and transistor sizes and examples of the integration levels. First one is SSI, small scale integration, 10 to 100 transistor. Example is logic gates. MSI means medium scale integration, 100 to 1000. Example is counters. LSI, large scale integration, 1000 to 20,000. Example, 8-bit chip. Next, VLSI, very large scale integration, so 20,000 to nearly 10 lakhs transistors. Example, 16 and 32-bit up. ULSI is, that is more chips, more transistors are embedded. Example is special processor, virtual reality machines and smart sensors. So these are all the integration levels. Next, design abstraction level. So here we are making the design abstraction. First one is system level. So that is the main system. Next, module level. What are the different modules we are using? For example, if you take a computer as a system, the module is different modules we are using inside the computer. Example, keyboard, mouse, CPU, these are all the modules. So inside the module we are using the gates. Next, inside the gates we are using the circuits. Next, inside the circuits we are using devices. Devices means in terms of source, drain, gate, terminals levels. So here we are using the device, P-type device, positive, and the N-type device is called negative. So these are all the design abstraction levels we are using. Next, Moore's law. So for every 1.5 years, the chip size will be doubled. That is called Moore's law. So from 1970s to 2010, what are the integration levels are updated based on the number of transistors and the speed. Because when we consider about the VLSI design, three parameters are important. One is speed, another one is area, and another one is power. So based on the three parameters only, we are defining the VLSI design. Next, why the name called MOS? M denotes metal. Metal is acted as a wire. O defines oxide. Here we are using maximum silicon dioxide. Next, we are using the semiconductor. Semiconductor, here we are using P-type or N-type semiconductor. So based on the metal oxide semiconductor, we are using the transistor level action. Next, two mode transistor action. What are the two modes we are using? One is enhancement mode transistor action, another one is depletion mode transistor action. So first, enhancement mode transistor action. You just take the example, water tap. Suppose if you open the water tap, the water will flow. That's the same thing. Suppose if you give the positive gate voltage, the current will be flow between source to drain. That is output came. And depletion mode means just you are closing the tap. Closing the tap means negative gate voltage you are given. So two type of transistor mode action here we are using. Next, activity, that's a small activity. So just notify the activity. So you note it in your notes and solve it. Next, enhancement mode and depletion mode transistor action. So here we are making the tabular column for the easy reference. First one is mode transistor, another one is gate voltage, because based on the gate voltage the channel is created. Channel means here we are making the channel. Through the channel only the current will be conducted. So the channel is very, very important. And next, on or off. If the channel is on, the current is conducted. If the channel is off, the current is not conducted. So first one, enhancement mode means positive gate voltage you are given means electrons will be flow in the channel. So the transistor is on. Next, PMOS enhancement. PMOS means P for positive. Positive means holes. Here we are using the holes. N means negatives. Negatives means electrons. So here PMOS means we are using the holes. So if the transistor is on, the threshold voltage Vt is equal to 0.2 VDD. So you can define 1 or 5 voltage. Next we go for NMOS depletion. So here NMOS depletion. Depletion means already we discussed negative voltage. So we are given the negative voltage between the gate and source. The transistor is on means VGS is equal to 0. VGS is nothing but gate to source voltage. So next, based on the mobility of electrons and holes, that is mu n, n type or p type means mu p. So the conductivity, mu is denoted for conductivity. So mu n is equal to 2.5 mu p. So NMOS is speed comparing PMOS. So the threshold voltage for depletion mode, that is VTD. VT is nothing but threshold. TD means that D denotes depletion mode. So less than minus 0.8 VDD, because depletion we are using the negative gate voltage. That only the minus denotes. Next, enhancement mode. So we define the transistor into three. One is enhancement mode, depletion mode, and another one is saturation or non-saturation mode. Here we are using the enhancement mode. No current flows, because if you are given the voltage VDS equal to 0, so there is no current is given between the drain to source. So the current is not conducted. That current is not flow through the channel. That is called enhancement mode. And the condition, just to notify the condition, VGS greater than VT and VDS equal to 0. So if VDS equal to 0 means there is no current flow occurred. Next, non-saturation. Here the non-saturation current, you have the condition VDS less than VGS minus VT. So just you are given the current just slanting the VGS minus VT. So the voltage level between DS, drain to source, is defined VGS minus VT. So the current is conducted in the non-saturation. Next we go for saturation, that is the constant current source. Constant current source means you are given the voltage increasing across the VGS minus VT. So VDS greater than VGS minus VT. So the train is pinched off. So train is pinched off means across the particular condition the train goes unconditionally. So the current will be constant. So it is called a constant current source, because based on the gate voltage you are controlling the current, because already we discussed in the first previous slide. So that is very important in the gate voltage. So based on the gate voltage only everything is defined. So this is the small example of basics of MOS transistor. Next we go for pwell process. So first we making the different masking levels. So the masking levels are defined into 8 levels. So first one is in the first diagram. So it is defined the pwell. The pwell is 4 to 5 micrometer. The outer layer is called silicon dioxide. So P denotes pwell, and opposite side here we are using the N substrate. So you just remember the keyword, same diffusion, different substrate. Substrate means that is a other downside layer, that is called a substrate. Diffusion, how can we make the diffusion means the outer layer of the silicon dioxide is heated and send the gas. Then it makes the bunk, that is called diffusion. Based on the devices P or N, we are making the gas. Next, the second one is we are making the thin oxide or thick oxide. That is thin oxide and thick oxide. Both are defined the transistor, that is drain or source. Next, we are making the polysilicon. Other layer is polysilicon. Polysilicon is mainly used for creating the gate, because our ultimate aim is we need to create the 3 terminal drain, gate, source. So here drain source is given based on the thin oxide, thick oxide, and polysilicon, that is making using chemical vapor deposition. So using the technology, polysilicon is deposited. Next, third diagram. From the third diagram, we are diffusing the P diffusion, because opposite to the pwell. So opposite to the pwell means we are using the P diffusion. Here the pwell, you see the diagram, above the pwell, that making the mask, that mask is called P plus mask positive, because if we are using the mask, we cannot diffuse any diffusion. So that is the main usage of P plus mask positive. That is the third diagram. And fourth diagram is just interchange. So interchange the masking level. Here P plus mask positive using in the third diagram, and fourth diagram P plus mask negative using. Then this side, the pwell side is open. Then you can make the diffusion N diffusion, because already I told the keyword same diffusion, different substrate. So if the substrate is P, N diffusion. If the substrate is N, P diffusion. That is the main concept you need to remember. Next we go for the PMOS different masking level. First one, pwell diffusion defined, and the second one thin oxide, thick oxide for P and N transistor. Next, third one, patternization of polysilicon using CVD. CVD is nothing but chemical vapor deposition. And fourth mask is P plus mask positive. Already we discussed P plus mask positive. It is defined for P diffusion. That is ANDed with mask 2. Because masking P plus mask negative both are ANDed with the mask 2. So next, fifth step, P plus mask negative. Next, sixth step, define the contact cuts. And seventh mask, define the metal layer pattern, that is metallization. And eighth one, overall passivation. Passivation means using the connecting the bonding parts. So that is for opening for accessing the bonding parts. That is called overglassing. So chemical vapor deposition and overglassing. Sometimes they are calling for 2 marks. So we need to remember the 8 masking levels from the pwell masking diagrams. So this is the pwell mask diagram using pwell inverter, that is CMOS inverter using CMOS pwell. So first you see the pwell. So inside the pwell you are using the well, ohmic contact well, and here opposite side we are using the, that is N-well side, that is PMOS transistor. So PMOS transistor using in N-well and NMOS transistor using in pwell. That is the 2 diagrams. So here we are using the VDD. That is VDD is nothing but power supply. Power supply, that is in the drain region. And next V1. So V1 is nothing but, that is the input side. That is polysilicon, we are given the input. And output is nothing but V0. Next VSS, nothing but ground. So you just remember the diagram normally. So CMOS is the combination of PMOS and NMOS. So PMOS means that is upper side. So if you are given the input 0, PMOS is enabled. If you are given the input 1, NMOS is enabled. Both are complement. That only it denotes the complementary metal oxide semiconductor. So that is called CMOS. So same thing here we are using the CMOS pwell inverter. Next, assessment. So making the assessment. The diagram, first one is from this mu n. Mu n is nothing but mobility of electrons equal to how much? Mu p. And next VTD. What is the derivation? And next, odd step of PMOS mask. So you just say the odd step of pwell mask, and next even step of pwell mask. So boys is just give the answer for pwell mask odd. Girls, you just note answer pwell mask level of even. Next, mass transistor, we are having the three regions, that is non-saturation. So non-saturation condition, what is the VDS derivation? That is the fourth question. And fifth question, define pinched off. So drain pinched off. These are all the 5 questions asking for assessment. So note it down. I will give you the time. So please note it down, the 5 questions, and let me answer. Okay. So you all must answer these assessment questions. Thank you.